Hello and welcome to the presentation and demo for Consolidated Multi-Cluster Kubernetes Ingress Services. My name is Bhushan Pai. I'm a Senior Technical Product Manager with the Network and Security Business Unit in VMware. When an enterprise wants to deploy a microservice application on a Kubernetes-like environment, apart from managing the Kubernetes infrastructure itself, they also have to manage the application traffic, service discovery. They need to secure the application access and also need a dashboard to debug and monitor the application traffic and its performance. A typical Kubernetes deployment looks something like this. They have ingress controllers running within the cluster. They have layer 4 load balancers to manage the load balancing for the ingress. They have GSLB for managing load balancing across multiple clusters or sites. In addition to that, they may have web application firewall to secure the application and have third-party DNS and IPAM. This makes the whole ecosystem very complex for operations and debugability. This also lacks end-to-end observability because each of these components might have their own dashboards. And end-to-end cloud-native automation is also very difficult. Avi provides a single consolidated solution to all of these concerns. Avi has a single product which does layer 4 load balancing, layer 7 ingress, web application firewall for security, GSLB for load balancing across multiple clusters and sites, and inbuilt DNS and IPAM, along with rich observability. And it provides all of this with cloud native automation, along with elastically scaling your load balancing fabric according to the traffic needs. Let's take a look at the general architecture of the Avi load balancer. So Avi has a very modern distributed architecture. There is a centralized control plane, while the actual load balancing traffic is handled by what we call service engines sitting in the data plane. Since the product is completely software, the service engines can elastically scale out and scale in depending upon the traffic needs. It can be deployed on any kind of ecosystem, right from a bare metal x86 box or a VM on a vCenter environment, or even as an instance in public cloud. As traffic flows through these service engines, it gathers hundreds of different analytics and metrics, which gets bubbled up to the controller, where it is presented on a dashboard for the user to help debug the application. In addition to that, the controller also uses these metrics intelligently to make scale out and scale in decisions. Specifically coming to Kubernetes environments, Avi has two operators to manage local and global load balancing. For local load balancing, we have AKO, which stands for Avi Kubernetes Operator, which translates all the ingresses and load balancer type services that get installed in a Kubernetes cluster to Avi virtual services and configures them on the Avi controller. The Avi controller in turn places those webs on the service engines to provide ingress load balancing. The second operator is AMKO, which stands for Avi Multi-Cluster Kubernetes Operator, which does the same across multiple Kubernetes cluster and configures global load balancing on Avi. And we'll see this in more detail in the demo and in the following slides. Let's talk a bit about the benefits of using NSX-ALB or Avi. The Avi controller is able to elastically scale the service engines according to traffic demands. As the traffic load increases, it can deploy more service engines, elastically scaling the load balancing fabric, and it can also scale down the service engines as the traffic load decreases. This provides an elastic load balancing fabric which scales on demand, provides high performance, and enables massive scale. Unlike other ingress services, which may provide VIP per ingress or a single VIP across all ingresses, Avi has a sharded model. As you see in the diagram on the right, user can predefine number of VIPs he wants per cluster, and depending upon the host name of your ingress, it gets mapped to one of those VIPs automatically. So this helps conserving the IP address space and is really useful, especially in public cloud environments where the IP address is a rare resource. Avi Controller has a inbuilt analytics dashboard which provides the application administrator a dashboard to troubleshoot the application performance, security, and end-to-end user issues. It provides real-time client insights right from the details of where the client is coming in from, which load balancer handled the traffic, and which backend pod was it load balanced to. Avi provides a single solution which works consistently across all ecosystem, be it on-prem or in public cloud. And since it's a part of VMware, we provide premium support, expert professional services, and education using knowledge base and hands-on lab available for all our customers. Let's take a look at the technical details of the solution now. We'll start with the local load balancing. So the local load balancing has these three components: Avi controller, which is the brains of the solution. There is Avi service engines, which provide the load balancing, and there is the Avi Kubernetes Operator, which runs as a stateless pod on your Kubernetes cluster and translates all the ingress and load balancer services to Avi virtual services. The deployment goes something like this. Day 0, you have your Kubernetes cluster, you deploy the Avi controller as a VM in your VMware environment. You configure the infrastructure cloud, which provides a way to discover everything within your infrastructure. For example, if your cluster is running in a vCenter environment, you configure a vCenter cloud, which allows the Avi controller to discover all the port groups, all the ESXi hosts and clusters in your vCenter environment, and allows it to automate the lifecycle of the service engines. Once this is done, your Kubernetes admin can go in and deploy AKO pod. AKO can be easily deployed using a Helm chart. And once this is deployed, it connects back to the Avi controller and your solution is ready for providing ingress and load balancing services. If you have multiple Kubernetes clusters, then the same operation can be repeated on each one of them. So essentially, you just need an AKO pod running on each of these clusters pointing to the same Avi controller, and the same service engine resource can provide application ingress as well as load balancing functionality to all of these clusters at the same time. Let's take a look at the application deployment workflow now. Once this cluster is ready, whenever an application developer creates an application with an ingress or a load balancer type service, the AKO gets notified because it watches on the Kubernetes API endpoint. It also polls regularly to do a full sync. It translates these ingresses, routes, and load balancer type services to Avi virtual services and configures them on the Avi controller using REST APIs. Avi controller then gets an IP address from the inbuilt IPAM and publishes the FQDN of the ingress to the DNS and places the VIP on required service engines, which provide the load balancing. Before we discuss this any further, let's move on to a demo. For the demo, I have a TKG cluster deployed on vCenter environment. I also have deployed a Avi controller. As the TKG cluster is deployed on vCenter, we have configured the infrastructure cloud as the vCenter cloud. We don't have any applications deployed right now other than the DNS virtual service, which will act as the authoritative DNS for all the virtual services that Avi creates. The first step in this is to install AKO. Installation of AKO is as simple as running a Helm command. So just a Helm install command and your AKO is up and running. So let's go ahead and deploy some applications. So for the application, what we deployed is a deployment, which will create the application pods. We have a cluster IP type service. We have a load balancer type service. And we also have a secret, which we'll use later. So in response to the load balancer type service, AKO creates the corresponding virtual service on Avi and adds the pods directly to the load balancing pool. As you see, the virtual service is created, but it's currently in a red state. That's because the Avi controller is still creating the service engines, since this is the first virtual service that got created. And we can see them being created on vCenter. As soon as the service engine gets created and they connect back to the Avi controller, the whip will get placed on the service engines and the application will go green. And now your application is ready to be used. So if you go and browse to the load balancers web, you'll see that the application is up and running. Usually applications are exposed using secure ingress. So that's what we are going to do next. Let's create a secure ingress for this application. So this ingress is going to use the secret certificate that we had created earlier. And as you see now, since the service engines were already up and running, the new whip automatically gets placed on the existing service engines and the application is up and running as soon as it's created. As you see, the Avi controller automatically assigns the virtual service the FQDN which is specified in the ingress spec, and it also gets an IP address from the IPAM and assigns it to the virtual service. It also syncs the certificate which was specified as a Kubernetes secret and applies it to the secure ingress virtual service. Terminating SSL on the virtual service does make the application secure, but in order to provide more security, a security admin may choose to apply web application firewall to the virtual service. Using AMKO, this can be easily done using a CRD created through the Kubernetes CLI. Let's take a look at what the CRD actually says. So as you see, the only thing that's specified out here is that for this application with this FQDN hackathon.ekg.vmware.com, we need to apply the WAF policy, hackathon WAF policy, which is pre-created on the Avi controller. And just like that, you see that the ingress, which was created before, now has WAF applied to it. We denote the WAF application by a shield icon next to the health of the virtual service. We can also verify the name of the policy applied in the virtual service details. As you can observe here, everything got configured from the Kubernetes CLI and nothing was configured directly on Avi controller UI or using APIs. Hence, this solution provides the application administrators a cloud native way of self-provisioning, load balancing, and ingress services for their applications. Now that we have seen how the local load balancing works, let's move on to global load balancing and multi-cluster load balancing. Like we discussed earlier, the operator for this is called Avi Multi-Cluster Kubernetes Operator, or AMKO. AMKO is a pod deployed on the GSLB leader cluster, but it syncs the applications across multiple Kubernetes clusters, and it creates GSLB services on Avi controller. The way this works is, say you have two different sites on which you are deploying the applications for HA purposes. You configure GSLB on the Avi controllers, tying them together, and you configure AMKO on the leader site. AMKO syncs the Kubernetes Ingress information from both the sites and configures GSLB on the Avi controller. Now that the GSLB service is configured, when the client makes a query for the FQDN of the service, the GSLB replies with the whip of the application from the correct site. Let's observe this in a demo now. As you see, on the Avi controller, I have configured GSLB with the local site, which is San Francisco, as the leader, and another site in New York as a passive follower. I have the same applications deployed on both sites, both on the San Francisco site as well as on the New York site. And now the application owner wants this application to be accessed through a GSLB service so that it can be load balanced between the two sites. For this, the first step is to configure AMKO. Just like AKO, AMKO also easily gets installed using Helm. By just running a Helm install command, we can install the AMKO pod on the leader cluster. Even this is bootstrapped using a values.yaml. In the values.yaml file, we specify various things that AMKO requires in order to sync across the multiple clusters. Here we have to also specify the cluster context for the clusters across which AMKO will sync the ingresses for a GSLB service. And we can also specify the traffic split between these sites. For example, here we are configuring 8:2 across the leader site and the follower site. Also, we can configure an app selector which allows AMKO to create GSLB service for only the ingresses which has this app label. As the TLS ingress that we had configured earlier has this label in its metadata, this gets picked up by AMKO and AMKO creates corresponding GSLB virtual service for it. As you see, it has added the member from local site and the New York site in the same GSLB service under the same FQDN of the app. If you edit the virtual service, you can even see that it has configured the traffic split ratio between these two sites as 2:8, which we had specified in the AMKO configuration. And with that, your global site is up and running. You can easily browse to the FQDN, and the GSLB DNS-VS resolves the FQDN to the correct web on the correct site. The Kubernetes admin can see these DNS resolutions in real time in the traffic logs for the GSLB DNS-VS. As you can see out here, the DNS was requested from this IP address to this GSLB VS IP for this host name, and the GSLB replied with the correct A record with the IP address of the web on one of these sites. Similar analytics are available even for the ingress service which we just created. We can see end-to-end timing, throughput, open connections, etc., and also the traffic logs for the transactions that we just did. But since this application was recently deployed and it does not have much traffic on it right now, let's move on to another demo setup that we have, which have similar virtual services. As you can see, the virtual service we are looking out here, Avi Demo VS, has multiple pools just like the Ingress virtual service. Each of these can have multiple pods in their pool. And just a bird's eye view can show you if something is wrong, why it's wrong. For example, one of the pod seems to be marked down because of the health monitor system HTTP. Each and every object on the Avi dashboard has its own health score. For example, the virtual service health score is calculated as a sum of the performance score, the resource penalty score, which shows if something is down, the anomalies penalty, which shows if the traffic is behaving anomalously, for example, if there is a certain spike or a DDoS attack. And then there is a security penalty, which shows how secure our application SSL is. For example, if you are not using recommended ciphers, or if your certificate is self-signed, or if your certificate is signed but is going to expire soon, it will show up as a penalty out here. All of these contribute to the total health of the application. If you click on the application, just like on the Ingress, you will see the analytics for this virtual service, starting with the end-to-end time, where you can see granularly the client RTT, server RTT, app response time, data transfer time across various time windows. You can even see throughput, open connections, connections per second, requests per second, HTTP versus HTTP2 requests, etc. On the logs, you can see traffic logs for each and every transaction going in and out of your application. And if you expand each of these, you can see even in greater detail. You can see where your traffic is coming in from, what type of device and SSL version your client is using, which load balancer actually handled the traffic, and which backend pool member it was load balanced to. You can even view each and every header field in the request and response, and all of this without running a single TCP dump. All of these analytics help you to easily debug your application. For example, if you want to debug why you're getting 404s on your application, you can just click on this or type it out in the search field up here, and we will automatically list all the 404s that are seen in your application. And then you can see that most of these or all of these have are for the same logo.png file. So maybe this file is missing on one of your servers. So debugging your application becomes really simple this way. To take a look at the WAF security analytics, let's move on to another virtual service which has WAF enabled on it, which is denoted by the shield icon next to the health. As you see, this virtual service is also getting a lot of traffic, and we have a WAF dashboard which shows a summary of all the attacks that are happening on your application. Basically, what path are getting attacked, what the client IPs look like, what are the main WAF rules that are getting hit. You can see these in more detail at per application transaction log level under the logs tab out here. As you see in the logs, you can expand any of these and immediately you can see what the WAF hit looks like and that it was actually rejected by the WAF. You can even expand the WAF logs to see which is the actual rule which got hit within the CRS group. The security admin can even add an exception for this rule if he thinks that this is an expected traffic and not actually a WAF hit. So as you see, not just applying the WAF rules to your application, but also editing those WAF rules to cater to your application needs becomes really simple. Thank you for attending NSX ALB's consolidated solution for multi-cluster Kubernetes services.